Alright, how's everybody doing? Hope everybody's having a good day today. Sorry for being a little bit late. Just finishing up dinner with the kiddos. Still feeling a little bit under the weather, but still getting better though. Feeling better. That's looking good. Look at the I still got my what you see in the background. I still got the 3D printer set up. I did some more 3D printing while I was playing around with it this morning and stuff like that. So just need to hear that. I was making started making, I don't know if you guys can see that. Started making little words and stuff like that. Yeah. I was messing around with Blender, see how to use Blender and saving the Blender files as an STL file, and then using that to boot up into the name of the program. I'm so new to all this 3D printing stuff. It's pretty fun though. My sister's fiance was over yesterday. He had dropped off a nice dinner table for me and the family. And while he was over here, he's the one who's big into 3D printing. He came over here to kind of readjust the 3D printer and stuff like that, tighten some of the specs down and everything on it. Because it was funny because when I had printed, I had done a couple prints. I had printed, you guys can see that. I had printed, looks like a focus. I printed that and a small little doggy right here, and it was funny. He says he was surprised how good those actually came out in comparison to how jacked up I had the actual 3D printer. It just wasn't. I didn't have nothing really. Let me see. Like the tolerances on it were all kinds of messed up. So whatever, it's still printed. But once he fixed it and tightened it down, we were able to do some. We did a couple of test prints that actually came out pretty decent after the fact. So that was pretty cool. So there's more to come with that. I was actually thinking about I get an idea on what I kind of want to do with some things for the stream and stuff like that. I want to make like and I seen somebody had something similar to what I want to do as an idea, but obviously I want to do it my way to make it, you know what I'm saying, a little bit different. But what I want to do is I want to cut a you know, like you would see like the images for, you know, how like Cisco Model Lab, GNS3 and stuff like that, and Cisco Packers, they use the quote unquote like images, just the models of a router and a switch and like a host and stuff like that. What I want to do is I want to cut those in Blender. Nothing fancy, but just cut them and just animate those in Blender, and then save those and then transport over those to the 3D printing software there, and then obviously print those out, put magnets in them, and then use them for when we do like whiteboard demonstrations and stuff like that, just as like a visual aid and stuff like that. I also have a couple ideas with a couple other things to add to, like there's some of the more common things we'll be using, and stuff like that. So I have some more ideas on what I want to do with it and how to incorporate this 3D printer into even into the CCNA study streams. You know what I'm saying? But that'll have to be something I'm gonna have to like just put a little bit more thought into stuff like that. But no, again, I apologize for running a little bit late. Again, I'm just, I'm still trying to get over what I got and stuff like that. So I'm just feeling, feeling a little bit under the weather, and yeah, that's it. So, I guess let's just let's dive right into it, guys. Just put this up to this. Then, let's open this up. This. Let's do a quick review, guys. Hello out there. All right. Let's do a quick review over some of the stuff we've gone over, especially about IPv6 and stuff like that. So let's dive into, again, this would just be a quick review, but I need to review what we've gone over just to keep this stuff fresh in our minds of IPv6. We're going to be going over and finishing chapter 25 today. So we're going to do chapter 22, 23, and 24. All right. That should be. We got 20 questions. Okay. All right. Which of the following is not a solution to the IPv4 address shortage? So which of the following is not? Okay. Doesn't look like we only have to select one answer. So NAT is the development of IPv6 is. Subnet broadcast addresses. More careful and reduced, so we're going to go with subnet broadcast addresses. Okay. All right. Which of the following, let me just pull a thingy on here. I want to make sure I'm monitoring YouTube as well, guys. I know you guys don't really chat on YouTube, but just in case somebody does. All right. Which of the following answers a valid abbreviation of the address? So let's write this out real quick. So we're looking for a valid abbreviation of this entire address. Now remember, we can always remove leading zeros. We can't remove trailing zeros. Okay, so it'll be 2000 :1 :2 :3. What else we got? So then we can do : and then 1110 :2200. All right, now let's take a look at what we got that matches that. Nope, that removed that 0 from there. We got to select 2 answers, so we got to select 2. So if they didn't remove the zeros from that one looks pretty good. What we got there? No, they removed those zeros. That one. Okay, so we got those 2 right there, guys. Okay, so we can select this one and we can select this one. Okay, all right, because what they did on, so this one they removed the trailing zeros, so that's invalid. All right, and then on this one they removed that trailing 0, so that's invalid. All right, Which of these is a correct representation of an IPv6 address? Which of these is a correct representation of a IPv6 address? That's wrong. So you can only do the abbreviation of the, you can only do this once with the abbreviated zeros with the double colon. So that's invalid. All right, so we can cross this off. 2001, yada, 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 yada. We'll go back to that one. That one doesn't look too bad. AD 61. 1, 2, 3, 4, 5, 6. Let me see this. 1, 2, 3, 4, 5, 6. That one's no good. And then what do we got here? And then that one's still good. All right, because there's no W, no WYZ. Okay, so what this is be the only correct representation of an IPv6 address. Okay, guys. See if we're right. Okay, we're doing good. All right. Host A is in one Ethernet VLAN. Host A is in one Ethernet VLAN, needs to communicate using IPv6 to host B. Which of the following close my server now. Which of the following which is in another Ethernet LAN? Which answer best describes the protocol used by host A to learn the layer 2 address of host B? Host A is in one Ethernet LAN and needs to communicate using IPv6 to host B. All right. Which of the following? So let's draw this out. So it looks like we got host. Let's say host A. We got host B. Let's communicate using IPv6, which is another Ethernet VLAN. And it looks like we got maybe a switch between the two. Okay. Say here's A. Here's A. Here's B. And here's our switch. That's W1. All right. And they're in different VLANs. Okay. Make some connections real quick. All right. So we'll say I don't know, VLAN 2 and this is VLAN 1, whatever. All right. So let's communicate with which answer best describe the protocol. So host A needs to learn the layer 2 information. Okay. We know that NDP, neighbor discovery protocol, is the protocol used in IPv6. All right, to discover layer 2 information, but that would only be applicable. Excuse me. That would only be inside of a actual. Say if they were inside their own actual domain group, so subnet domain group or subnet. All right, this is actually they're divided on two different VLANs. Okay, so the switch here that's probably doing some layer 3 switching and stuff like that, that would be where the layer 2 information is being held right there. So no protocol is used. A does not learn B's MAC address. We're going to go with that one. Let's see how we do. All right, we're good. So that was the answer. So this device here, the switch that's doing this switch right here is holding all that layer 2 information right there. Okay. All right. Which of the following answers are true about the rules for abbreviating an IPv6 address? All right, select 2 answers, okay? Which are the rules for abbreviating an IPv6 address? Multiple consecutive groups of zeros between 2 colons can be replaced by : in one location only in the address. In one location in the address. And that's true. All right. So we'll put, so this one's looking pretty good right now. Okay. Trailing zeros within a set of 4 hex digits between colons can be removed. Trailing zeros? No. We're looking for leading zeros. All right. So we're going to say no on that. Abbreviating is the process of making an IPv6 backwards. No, it's not. Cross that out. Multiple consecutive groups of zeros between 2 colons can be replaced with colon. No. Remember, it can only do it in one location. Leading zeros within a set of a 4 hex digit between colons can be removed. Yes. All right, so we're going to select those 2 answers. So we'll select this one, and we'll select that. All right, we did pretty good. All right. IPv6 represents a binary IPv6. IPv6 represents a binary IPv6 address using hex characters. Which of the following binary strings represents C and E? What represents C and E? Okay. Again, we can kind of cheat here. We're looking for C and E. Okay, and we want to go to binary. So this would be the binary representation of C and E. Okay. All right. How many subnets can be represented in? How many subnets can be created from one hex character in an IPv6 address? It's 16. All right, and that's because hex goes from 0 to F, which is pretty much 16. Is 16 characters. So 0 all the way to F is 16 characters. Okay. All right. And if you don't remember, we've gone over this, and we can just draw this real quick. All right. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. Come up here. 9, 10, 11, 12. Wait. Oh, see, oopsie poopsies. It should be A, B, C, A, B, C, D, E, and then F. Okay. All right. Obviously, and then if you can think about these in easier terms, this is pretty much like what it represents, guys. All right. So it's starting from 0 all the way to 15 gives us 16 characters. Okay. Okay. Examine the output of the show IPv interface brief command shown in the exhibit. What 2 address types are shown? All right, so we have a link local, and then we have a unique. All right, so we have a unique, so a link local, and then a unique local. Okay, that's represented by the FE, which is link local, and FD representing unique local. Okay. Okay. Which of the following describes the specific address range of a address range typically used by the ANA global IPv6 address? So we have the 2000::-2. I believe that's the range right there. Which of the following describes the specific. All right, I believe it's the ::/2, the 2000::/2. Oh, we're wrong. It's the ::/3. That's a tough one to remember. What's up, Meridoxbet? /3. I know. I keep biffing. Again, IPv6 is one of those tough ones for me, man. So my boy Meridoxbet, congratulations too, by the way, man. It'd be the : /3. All right. Thank you very much, man. I appreciate that. All right. Which IPv6 address? Which IPv6 address represents a global IPv6 address? So which address represents a global IPv6 address? Okay. So FE, remember, link local. All right. So we're gonna go up here. We're gonna select two answers. So we can select this one. No, we can't select the one because that's the DV8. So it'll be this one, right? Go with those two. All right, we were right. All right. If your ISP assigns you a prefix, yada 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 /56, how many bits do you have to create your subnet? So remember, so the almighty prefix that's the most common is the /64 bits. So if we 50 pretty much 64 minus 56, how much would we have left? All right, so that will give us again, so that'll give us eight bits. Okay, that'll give us 8 bits to create subnets with. Okay. All right. Identifying the first hex digits for a link local address in an IPv6 network. Identifying the first hex digits for a link local address in an IPv6 so that'd be the FE80. All right, the FE80 represents the first hex digits of a link local address. It'd be the FE80. Okay. Based on the following configurations, what would be the assigned global unique address? Based on the following information, what would be the assigned global? All right, so what do we got? All right, so remember, so this is where we got to do some of that conversion type, okay? We'll do this real quick. All right. So what do we got? We got 2005 : and then it's in the 88th bit. All right, in the 88th bit, which gets us to all right, so we're looking at this. Can already kind of narrow it down to a couple of these real quick. It's not this one. Not this one. We're at the 7th bit. Oh, it's this one right here. It's funny is they didn't invert the bit either on this one. Because it'd be we're gonna go with this one right here. Ah, how did I go wrong? Yeah, you were right. But how did that? Does that turn? Oh, because 2 turns into 0. Damn it. Because 2 turns into 0 right here. Oh. And then that's why that's be a 0 right there. Yeah. Okay. That one always gets me. So what it does is because this 2 right here, this 2 right here, that turns into a 0. It inverts to a 0. So obviously if that inverts to a 0, then you have 0, 0, 0. All right. And then colon, then that's why it's 8395. As you can see from this address right here, how it's the 0, 83, FE, FF, FE 95264. Man, IPv6 is something else. The R1's interface has the MAC address of yada yada yada. What will be the IPv6 generated? What would be the address generated by the router if you configure the interface to use the? All right, so this is MAC address. R1's MAC address. What would be the IPv6 address? That's usually. Is this asking for link local? Is this asking for link local? Could be asking for link local. So if it's asking for link local, then it's one of these 2 right here. The FE80. And then the 2, then the 0 here would convert to a 2. Right there. So if that's the case, FF. Yeah. All right. So we're gonna go with this one right here. Woo! All right. All right. Got it that time. All right. Yada yada yada. All right. What can be determined by this output? IPv6. So there's our link local address. All right. There's our group of join groups. Select 2 answers. The interface will not participate in duplicate address detection. The router is not enabled with. Yes, it is. Yes, it is. The link local address is not likely using the default. Not using the link local address is not using the default. Actually, it might be. It's like 2 instance interface, but not the first address detection. Host uses stateless autoconfig for addresses. This is a tough one. You can use, it's not using the, because you would see that right there. And I can't tell. All right. What are those two? Huh. So it's running ERGRP. How do we know it's running it? Tell me. All right, that was a tough one. Traffic, multicast group, 5 and 6. Oh, it's because of this information right here. Man. Tell you, IPv6 is something else, man. Like in a way it's simpler, but in a way it's like so much more complicated. What statement is true about the IPv6 unicast routing command? The command is required for the IPv6. The command is required for the interface. Yes. Okay. Ah. I guess it's right. Right. Gives you almost the same answers for both of them. All right. Based on the configuration, man, I'm doing really bad on this one. Based on the configurations provided below, what would be the address? What would be the assigned link local address? Again, so we'll have to, so the link local. So this one would turn into a 2. So we have the FE80 2. No. 82 delta. All right, so it'll be this one right here. At least we're getting the hang of that one so far. So we're getting that one. That's why we have to do these reviews, guys. Given the global unicast address, yada yada yada. What would be the solicited node multicast address? So solicited node multicast address. So we want the Epic, epic, epic. This is why. God, IPv6. The solicited multicast address is used to send traffic to limited subnet locations. One common use neighbors. These RFC specific of the first 104 bits of the address always. Yeah, with the first last coming from the IPv6 address. This means the device configured with the struggle with me and Network Plus practice exams. Hi, Lady Web. How are you? Man. So what did I go wrong on this one? Ah, I see what I did wrong. It's because it's the last 104 bits, right? So that gets it there. Alright. Man, I swear IPv6 will beat you up. Will eat you up and spit you out. Alright. Router R1 on the fast Ethernet 00 interface was up and working and was configured and was then configured as follows. Interface. They did the MAC, alright, and the IPv6 address. Which of the following unicast addresses would now be included in the output of the show IPv6 interface? Select two answers. So that would convert to a 2, right? Yeah. 1, 2, 3. And then the link local. I'm okay. I'll keep missing the cabling. 802.1. 802.1 let them stand for frequency and distance. I swear to God, that's the only question on the exam. Like over half. I feel you. I'm getting beat up today with IPv6. IPv6 is tearing me up a new one right now. All right, and let's go with our link local address here. Ah. All right, the global unicast address would be exactly configured. Link local. Using the modified. Yep. FML, I'm scared now. Yeah, IPv6 will tear you up. It's beating me up right now. It is beating me up right now. I tell you, IPv6 is one of those things like again, in a sense, it's like it should be easier, and it is. It's just getting over the hurdle of trying to like unforget about IPv4. That's making it, at least for me, it's making it so hard for me to just grasp some of these basic addressing concepts about IPv6, because it's different. It's different. Again, it's simpler in its way, but again, it's just totally stinking different. That's making it harder for me to like wrap my brain around it. All right, so let's read how we got this wrong. So the global unicast address, yada yada yada, would be the exact, would be exactly as configured. Cool. The link local address using the EUIE/64. So that's where we got right, because so the link local address by default will always use the EUIE format. I just took us on the assumption that by doing this, and I'm wrong. I know I'm wrong, but I took the assumption that it was just going to use the EUI default, but it doesn't. It just uses the global unicast as that address, which that is a valid IPv6 address. I just overthought it. How's that? Stinking. All right, based on the exhibit, which two solicited node multicast addresses will the router create? All right. What two addresses will the router create? There's our link local. There's our global. Right? You and me both. I think I'm. It's like sometimes I think I'm further ahead of where I actually am sometimes with this stuff. You know, you take one step, you take a whole bunch of steps forward, and then you do one of these practice exams, and then it knocks you back down a couple pegs to make you remember you ain't ready yet, Captain. I mean, we're making big strides, you know, but it's just again, it's things like these that I just got to spend so much more time on to really wrap my brain around them. All right. Right. Based on what two solicited node multicast addresses will the router create? What two solicited node multicast? Multicast. So we're thinking multicast. What will it create? Oh boy. And I am stumped on this one, like a stumpy tree. Hey, we got those two right. Yes, I'm struggling with network exam. I consistently getting 55 a review, and it always calling Wi-Fi standards. A few security plus questions. It's a mix-up, right? So when you do your practice exam, are you doing the whole entire CCNA, like the whole entire broad scope, Lady Web, when you do your practice exams, or do you do it like subject by subject? Like this one, I just broke it off into these 3 chapters that we just did. Woo! That is not a good score. You do it all. Have you finished reading? Well, did you read the? Have you gone through the whole entire official cert guide? Did you even use the official cert guide to do all of your training, or did you just do off of CPT nuggets? Make this one shorter. Which are the following? All right, so we know this one. Identifying the first hex digits. First hex digits of like local, based on the exhibit, solicited node. What would it create? So it'd be the 2F2s. Based on the of network plus strictly the CPT nuggets. So are you going after the CCNA or just the Security Plus exam? Based on the following configurations, what would be the assigned global unicast address? And this is where I got that one wrong. Let's get a couple of what are we gonna be making here today? So let's get a couple of routers fired up real quick, guys. That way we don't have to wait for these routers to take too much time to wasting getting them booted up. We'll make a topologies just like the book has. Network plus exam, and all I need to pass class. I've done. Keep following practice, so I haven't taken the real one. Once I get the cert, then it's CCNA time. To pass class, done. Network plus exam, all I need to pass classes. Done. Keep following. Oh, so are you? Oh, so I mean, just on it. So are you taking the Network Plus just for? Is it for a class? Are you Are you going to college right now? For it or something? Or some kind of degree program or something? I know I'm going. I'm in. I go to University of Phoenix, and I'm going after a bachelor's in IT. It hasn't specified if I needed any of the certs or anything like that. This one. See. See 1, 2. Oh, that is what. This is what. Oh, okay. I got you. I got you. I got you. How in depth is the Network Plus? Um, that's Network Plus. That's by that's a what is it? That's by CompTIA, right? Network Plus. These fired up. All right. Those would be give those a couple minutes to cook. Yeah, that's cool. But while those routers cook, let's get into chapter 5 here. Chapter 25, I mean. Implementing IPv6. Now, we've already gone through like IPv6 routing. We've implemented OSPF version. We've implemented OSPF version 3. We've also implemented DHCP version 6 in a lab. We're gonna go ahead once these routers fire up. We'll do the same thing. We'll implement OSPF version 3 again. So you guys we can go over that configuration again, because remember the implementation of OSPF version 3 with IPv6 again is very similar, but is a little bit different. Okay, same thing with DHCP version 6. Again, is similar, but again very different. We're gonna keep with the kind of addressing that we did before. Again, that addressing was very simple in a way, and it's going to help us keep this um, simple, but um, we're gonna we'll have to see what this chapter is getting into, because I can already see that it's going to ask for default routes, network routes, host routes, and floating static. So it's going to be similar to how when we were in an IPv4 and we were implementing static floating over OSPF and all that because of the different cost, um, the the administrative cost there. No, administrative is it administrative distance? Administrative distance, um, and what that represents when we're routing. So, all right. So this last chapter, part 7 here of the book completes the material about IPv6 by explaining 3 major topics. The first section of IPv6 connected in the first section examining IPv6 connected and local routes similar to IPv4, showing how a router adds both connected and local routes based on each interface. The second major section of the chapter then looks on how to configure static IPv6 routing by typing in commands, and this causing the IPv6 route command instead of the IP route. So IPv6, we're using the IPv6 route command instead of when we were using IPv4, we were just simply using the IP route command. All right. This final major section examines the neighbor discovery protocol, so NDP. So remember, NDP replaces ARP. It replaces address resolution protocol. Okay. NDP is what IPv6 uses instead of ARP as an IPv4. Okay. So neighbor discovery protocol. Okay. All right. Let's kind of just take a look at, do I know this already quiz real quick. All right. A router has been configured with an IPv6 address, yada, yada, yada. Command on its gig 0-1 interface as shown in the figure. The router creates a linked local address, FE. So remember the FE80, that's always representing, when we see that the FE80, that's always representing the link local addressing. Okay. The FE80 : Foxtrot Foxtrot : Foxtrot Echo 00:1 as well. The interface is working. Which of the following routes will the router add to its IPv6 routing table? Okay. Choose 2 answers. All right. What do we got? Router has been configured with the IPv6 address on its gig interface. Router creates a link local address as well. That's what we're looking at. Hmm. Man, I tell you, man, this stuff really it makes my head warp sometimes thinking about IPv6. Just hurts your brain. It hurts your brain. The router creates a link local address, yada yada yada, as well. Cool. The interface is working. Which of the following routes would be added to the IPv6 routing table? So I'm guessing it's still talking about router 6. Go with A. And then go with A and B. Probably going to be wrong. Let's just go with those two. All right. A router has been configured with the IPv6 address, yada yada yada, command on its gig 0-1 interface, and IP address, yada yada yada, on the gig 0-2. Both interfaces are up and working. Which of the following routes would you expect to see in the show IPv6 route connected command? Both of them. I'm kind of curious. I mean, we can get rid of these addresses afterwards. But I guess where it's trying to get me, I'm just gonna go with A and C on this one too. I'm gonna go with A and C on this one too. Go A and C. All right. An engineer needs to add a static route IPv6. Needs to add a static IPv6 route with the prefix yada yada yada. To route R5's configuration in the figure shows in the figure shown with question 1, which of the following answers should the valid static IPv6 route for that subnet? Oh, it wants to get to the 123. So the 123 off of R5, so to be off S0, be that 011, right? Right here. So to be A on that one. So 3, that's a good one. So 3 to be A. All right. Go back here. This is up now. Run it slow as heck. let's just go into its gig 0-0 interface, and we're just going to hit it with the IPv6 address. All right, and then we'll just go into let's do a do show IPv6 route. So we were right. So it's just gonna, oh wait. So this is where it gets a little confusing. So on the logo, so you see how it has the 128. So it's covering the whole entire that subnet, that network. But it also has the connected. Oh, so that one's definitely wrong. That one's wrong. So we were right. So it is A and C. All right, it is A and C. Now, if that was a 1, instead of that being a 2, that one would be right too. All right, so this one is actually, so we're good on that. This one is what, so if a router has been configured with that address, owns router correct to link local addresses. That one we'll just we'll keep it moving from there. Keep moving. All right, so let's go down to number 4 now. An engineer needs to add a static IPv6 route for the prefix, yada yada yada. For our find the figure shown in question 1, which of the following answers show a valid static IPv6 route for the subnet on R5. So where are we trying to get to? Route to the prefix, yada, yada, yada. So we're looking for the 2001 6. All right, let's go with A on that one. We'll go with A2. An engineer types the command IPv6 route, yada 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 yada. 129. Configuration mode and press enter is later. A show IPv6 route command does not list any routes for the subnet. Which of the following should have caused? Which of the following could have caused the route not to be to the command? The command should have been using a not next hop address instead of a global. The command is missing the outgoing interface parameter. The router has no routes for the route for the distance exists. The command output shows 2 routes for the longer output of the show IPv6 route command, which of the following. All right, that's so. That's OSPF. Oh, he's giving it the administrative distance of 129. A route for exists. Later this, which of the following could have caused the route not to be? Oh, I think I know what's going on. This might actually be C. This actually might be C. So let's preliminary write a C there. And then we'll 5 we'll put an A. All right. The command output shows 2 routers from a longer output. The show IPv6 route command. Which of the following are true about the output? So the show IPv6 route static. Yada yada yada. Which of the following are true about the output? The route to ::0/0 has been added to the IPv6 routing global command. The administrative distance. The route to has been added to the interface. We have to choose 2 answers. So C. C and D. C and D. C and D. All right. PC1 and PC2 and router R1 all connect to the same VLAN and IPv6 subnet. PC1 wants to send its first IPv6 packet to PC2. Which protocol or message will PC1 use to discover the MAC address of two PC1s? Should send the frame with the encapsulated IPv6 packet. PC1, PC2 are all connected in the same VLAN and using IPv6. PC1 wants to send its first IPv6 packet to PC2. Which protocol or message will PC1 use to discover the MAC address to PC1? Should send the Ethernet frame that encapsulates the IPv6. NDP. Boy. Let's go with B. B. All right. Ooh. All right. Which of the following pieces of information does a router supply in the NDP router advisement? So router advisement message. So which of the following information does a router supply in a NDP router advisement message? Which of the following routers IPv6 addresses, host name of other routers, prefix length, router advisement. Let's go at A and C on that one. See how many we got wrong here. All right, so this should be a C. This section we got good. We got that one right. That one's good. 4, ooh, 4 we got all wrong, all kinds of wrong. And then 5 is wrong. This should be C. This is all kinds of wrong. A and B. That one's right. That one's right. So we didn't do too bad. But let's go take a look at where we went wrong. A and B. So that's been added to the global. They should a distance of 1. Okay. The router has no match for. Okay. And then, how does that make sense? Oh. All right. We got a little bit beat up on that one. Not too bad. clean that up real quick. Just wanted to clean that up. I'm gonna go grab my coffee pot. Hey. Just grab a coffee. All right. Just cleaned up that real quick. Man, I might have to do like a whole nother stinking review all the way back to the beginning of IPv6. It's like I don't feel like it's stuck too well. All right. Connected and local IPv6 routes. A Cisco router adds an IPv6 route to its IPv6 routing table for several reasons. Many of you could predict those reasons at this point in the reading, in part because of the logic mirrors the logic. Logic mirrors the logic. Routers used for IPv4, specifically a router adds an IPv6 route based on the following: configuration of the IPv6 address on the working interface, connected and local routes. All right. The direct configuration of a static route, the configuration of a routing protocol like OSPF version 3 on routers that share data links, dynamic routes. The first two sections of this chapter examines the first of these two topics, which discussions of IPv6 routing protocols now residing in the CCNP enterprise exam. Okay. Rules for connected and local routes. Routers add and remove routes and local routes based on the interface configuration and the interface state. First, the router looks for any configured unicast address on any interface by looking for the IPv6 address command. Then, if the interface is working, if the interface has a line status up, the protocol status is up. Notice that the output of the show interface command, the router adds both a connected and local route. Note, routers do not create connected or local IPv6 routes for link local addresses. Okay. The connected and local routes themselves follow the same general logic as with IPv4. The connected routes represent this subnet connected to the interface, whereas the local route is a host route for only the specific IPv6 address configured on that interface. As an example, consider a router with the following working interface configured with the IPv6 2000::1 with the 2000:1:1:1/64 command. The router will calculate the subnet ID based on the address and prefix length. All right, and its own place, and it will place a connected route for that subnet, the 2000 yada yada yada, into the routing table. So the router will calculate the subnet ID based off the address and prefix length. It will place that connected route for that subnet, okay, into the routing table. The router also takes the listed IPv6 addresses and creates a host route for that address with the prefix of 128. Okay, so that's where something I was getting, I guess, a little bit confused on. The router also takes the listed IPv6 address and creates a host route for that address. So it creates a host route. That's why when we were seeing the 128 So it would be the 2000:1:1:1/128. So that is the host route for that address with the 128 prefix length. With IPv4, host routes have the /32 prefix length, while in IPv6 they use the 128 prefix length, meaning exactly that one address. Okay. All right. The following list summarizes the rules about how routers create routes based on the configuration of the interface IPv6 unicast address for easy review in the study. All right. Routers create IPv6 routes based on each unicast IPv6 address on an interface as configured with the IPv6 address command as follows. The router creates a route for the subnets as connected as a connected route. The router creates a host route with the 100/128 prefix length for the router's IPv6 address in a local route. Routers do not create routes based on the linked local addresses associated with the interface. Routers remove the connected and local routes for the interface if the interface fails, and they re-add the routes when the interface is again up in the up state. Okay. All right. Just trying to wrap my head around things real quick, guys. All right. Example of connected IPv6 routes. While the concept of connected an IPv6 route works much like IPv4 routes, seeing a few examples can certainly help. To show some sample routes in the figure gives details of samples internet used in this chapter. The figure shows an IPv6 subnet ID. The upcoming examples focus on the commands of the local routes on R1. And this is it's just showing you for the example of the different subnets here. All right, so let's jump over to Cisco Model Lab and start building this. All right, this should be pretty easy. That way we can kind of follow along. Zero, 1, 2. Very good. And we're going to use the same exact addressing scheme here, okay? So the 2001 deviate colon 11111 colon 1, and then interface that. Now we can do show IPv6 routes. And then remember, so the host route right there, that's where we're seeing the 128. And then we have our our connected routes. Holy stuff. Notifications are crazy. All right. Then we can come over here. This is the -4, so that's 2001, DB8, 111, colon, 4, right? 4, colon, 2/64. Shut. And then that's the -2. So interface 801. It's the -2. Six addressing 2001 colon DB8 colon 111 colon, and then this is the -5, right? Colon 5, yeah, colon 5 colon 2/64. Got. It's gonna come up, and then that is the colon 3. Yeah. It's just the same. Yeah, okay. All right, to clarify the note in the figure, note that the figure shows IPv6 prefixes, IPv6 prefixes, subnets with the shorthand notations. For the interface, IPv6 address in the figure shows the abbreviated ID portion of each interface across each address near each interface. For example, yada 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 begins with the ID value and added the colon 1. Yep. Okay. Now on to the example of connected routes. To begin, consider the configuration of router R1s from the figure. The excerpt to show running config command shows 3 interfaces, all of which are working. Also note that no static routes or routing protocols configurations exist. Let's go back here. We'll do the run. have our 3 interfaces with no other routing protocols or anything like that. So we haven't implemented OSPF or anything like that. Okay. Okay. Yep. So again, to go back to our show routes, they're exactly the same. All right, we don't have, and again, we're not using any routing protocols or nothing like that. All right. All right, so we haven't configured any of that. All right, all 3 highlighted routes show that show the same basic kind of information. So for discussion, focus on the first pair of highlighted lines, which details the connected routes for the subnets, yada yada yada. The first pair of the highlighted lines, the route is directly connected to the route. The interface ID is gigabit 0-0. Prefix and length is the DB8 yada yada 1/64 on the far left. Connected C identifies the route connected to the route per the legend above. Also note the number in the brackets. Mirror the same ideas of IPv4 show IP route command. The first number represents the administrative distance, and the second represents the metric. Okay, so let's do the do show IPv6 route again. All right, so the first number represents the administrative distance. Obviously, this is connected, which is 0. It's the most believable, all right? And then the next number represents the metric, 0 representing it's connected. Okay, so it's the most believable it can be, okay? All right. Yeah, we'll even see, let's see if we can even do ping, 2001. 8 1 colon it'll have to be 4 colon 2, right? Yeah, okay. Then if we wanted to ping router 3, that's 5 colon 2. Okay. So we can ping router 2 and router 5. Okay, those are both up and up. Okay. All right. All right. So let's continue on. Also note, yep. All right. Examples of the local IPv6 route. Continuing the same this example, these three local routes should exist on R1 for the same 3 interfaces as connected routes intended. That in this case, no extra local routes for other purposes. Show only local routes as listed in the show IPv6 route local command with the local. So let's do that command. Do show IPv6 route local. Again, there's our three local routes. So the :1, the :4, and the :5. All right. So the :1 is this network right here. This link to R2, that's the :4. This link to R3 is the :5. Network right there. All right. For the highlighted, look at a couple quick facts. First, look at the R1's configuration in the example. Um, this local route exists. This local route lists the exact same addresses. Yep. All right, so it's just again, it's listing the local routes. Okay, so the actual what's local to that router. That's why it's having. That's why it's showing it in this prefix. So it's local to this router. Okay. While the show IPv6 route local command shows all local IPv6 route, the show IPv6 route connected command shows all routes. So if we run the connected command, all right, and that's where we get the, all right, so that's where we get the prefix /64 now, and it's showing us these are, so instead of it showing the local host, showing the connected routes now. So not the local host routes, it's showing the connected routes now to each one of these areas. So this area and then this area right here. Okay. Woo, don't zoom out. Static IPv6 routes. While the routers automatically connect in the local routes based on the interface configuration, static routes require direct configuration with the IPv6 route command. Simply put, someone configures the command. The routers place the details in the command into the route in the IPv6 routing table. The IPv6 route command follows the same general logic of as does for the IP route command, as discussed in chapter 16. For IPv4, the IP route starts by listing the subnet IDs in mass. So for IPv6, the IPv6 route begins with the prefix length. Then the represented command lists the direction of how these routers should forward the packets towards the destination subnet or prefix by listing the outgoing interface of the address of the next hop router. The figure shows the concept behind the IPv6 route command, demonstrating the concepts behind the static routes on R1 for the subnets to the right, subnet 2 or the point 2, all right. A static route on R1 for this subnet will begin with IP route yada 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 /64 followed by the either the outgoing interface or the next hop router's address. Okay. Let's come over here now. All right, let's do IPv6 DHCP pool. We're going to call it net2 on this one. All right, address prefix. All right, and that's 2001 colon DB8 colon 1111 colon 2. All right, colon /64. Do the same thing on this one too. All right. 6 DHCP pool, call you net3. Address prefix. All right, same thing, colon 0 2001 DB8 colon 1111 colon 3 colon /64. Crazy lights going like crazy in this room. Let's make some connections. This light's gonna give me a seizure. Oh. Swear this light's blowing. It shouldn't be blowing. It's one of those 20-year lights. And it's already blowing. All right, let's do that on this one too. Exit out of here. Then we'll do IPv6, DHCP, pool, let's say net1, address prefix, 2001, DB8, 1.1, colon, 1, colon, slash. We got our addresses, so we're pretty good. Let's just make sure we got our addresses on every PC. We're looking good. Our addresses are in the right ranges, so that's a plus. The only thing I've done so far is I've just enabled DHCP, just for dynamic addressing purposes on these host PCs here, guys, okay? I haven't done anything with static routes or dynamic routing protocols or anything like that, okay? Because we're going to be going over static routes and stuff like that. Just want to make sure that this PC gets a valid address. And it did. All right. So all of our addressing is looking pretty good right now. Okay. So what we need to do now is we need to build a static route so we can get over to the :2 network, okay? So we need to do the IPv6 route command, all right? All right, followed by either the outgoing interface or the next hop router address. All right, so let's go back to R1. All right, and we'll do the do show IPv6 route again. So you can see we don't have anything dynamically configured in there or statically configured. It's just what it is right now. All right, so we're gonna go with the we'll go with the next hop router command. So to be IPv6 route, and we're looking to go to the DB8.2, so that'd be 2001 DB8 colon 1111 colon 2 colon slash 64. Okay, and that'd be via the 2001 DB8 colon 1111 colon 4 colon 2 Now we can run the, let's run the IPv6 route again. All right, now we have a static route. All right, so now we should be able to ping. Yeah. We should be able to ping PC2 now. So we're able to ping PC2 now, okay? All right, and that's because we just built in that static route using the next hop router's address, okay? All right. Just like we would do in IPv4, all right? So we have an administrative distance of 1, all right, with the metric still at 0, okay? All right. All right, static routes using the outgoing interface. All right, and so now what we'll do for this network, so that's the 3 network, okay? And that is gig 02. Yeah, so it'll be IPv6 routes. All right, and we're going to the 3, so it'll be 2000 through 2001, EV8 colon 1111 colon, that's the 3 colon slash 64 net. All right, and we're going to be going it out the gig 0-2, going out the gig 0-2 interface, okay? All right, so let's run the do show IPv6 routes. All right, we have another static route here. All right, another static route here for the 3 net going out gig 2 on R1. So let's go over to PC3 here. Let's copy its IPv6 address. And now let's see if we can ping PC3. No. Let's erase this. Let's confirm it's erased. Okay. All right, we erased it successfully. Now let's do that again. IPv6 route. IPv6 route, and again 2001 DB8 colon no 111 colon 3 /64. Now let's do it as the next hop, and we'll just see if that works now. And that is 2001 DB8 colon 1111 5 2. Okay, now let's just confirm. Do show IP6 routes. Good. So let's do a do. None of that worked. But it didn't work. It did not work. Let's erase that again. All right. Let's confirm that's erased. All right, we'll even try to ping it now. Pings failed. All right. All right, so let's do that again. IPv6 route. All right, and that's to the net DB8 colon 1111 colon colon 3 colon /64. That is out the gig 0-2 interface. Do go IPv6 routes again. All right, now we have that route again, going out our gig 0-2. And it fails again. That's why I hate doing static routes sometimes. Static routes hate me sometimes. What's up? Kaga! What's up, my friend? How are you doing? Don't know if I pronounced that right, but what's up? We're going over some IPv6 routing today, my friend. Fun times. Oh, snap! Good looks on the follow. Thank you very much, Kaga. How we doing today? So what we're using is depending on your familiarity with stuff, we're using a program called Cisco Modeling Lab. You might be familiar with it. We're going over implementing IPv6 routes here. What we're chasing after is we're going after the CCNA. That's the Cisco Certified Network Associate exam. We're studying up for that exam. So currently we're almost done with the first book here, and then diving into the second book. And the last chapters of the first book is about IPv6. If you're familiar with anything IPv6, it's fundamentally similar to IPv4 for the most part. Obviously there are some changes that were made to make sure that IPv6 works. Just because of the larger address groups that obviously IPv6 has, with its 10 octillion addresses, in comparison to IPv4 with its couple, with its it has, IPv4 has multiple million addresses. I think altogether, well, yeah, I mean altogether, if you go all the way down to the very zero, the very last, you have about 4 billion addresses. I passed the CCNA Zoom setting for the same things. Oh snap! That's what's up. So how far are you along? How far are you along with your study, and like what part are you at within your study? Super curious to know. Or are you exactly right here where I'm at with IPv6 and stuff like that? IPv6 has been kicking my. I understand it, but it's like the subtle nuances to IPv6 that have just been kicking my butt lately. Mainly around their some of the terminology used around, like multicast, link local, stuff like that, and then understanding, like I understand link local, I understand unique local, global addressing and stuff like that. But once you get into like multicast addressing and stuff like that, just because of the differences, it's like I'm trying to rewrite my brain to get out of the idea of IPv4 and trying to just think about IPv6. And I think that's where I keep like stumbling over my own self. In a sense, and it's true too, and they say it, in a sense, understanding IPv6 is a simpler concept, in a sense. But it's mainly because I have, in the beginning of all my studies, I've focused so primarily on understanding IPv4 that now trying to re-understand IPv6, it's like trying to rewrite my brain all over again. So what we got going on right here is I've made a simple topology, just using yeah. Yep. That's what we're trying to do here too, is just get some practice with it. So this lab right here that I built, this is primarily just using IPv6, nothing IPv. So we're not dual stacking anything, nothing like that in this lab. The only thing I've implemented is DHCP version 6, just so our host can have addresses. That's the only thing we haven't. I haven't implemented OSPF version 3 or anything like that on these routers. So we're just going over statically configuring these routes on these routers here. But one thing that's we're having an issue with is statically configuring a route via an interface. What just happened out there? Yeah, it's just one. What was that? So, can you close the door?
So how's the stream going?
Going pretty good. Studying Ethernet channel and HSRP. They are modules for the switch from the switched networks. Yep. So we did. I covered. It was a couple of streams ago. I was covering Ethernet channels and stuff like that. It was funny because I kept breaking Cisco model in Lab 2 with I kept breaking Cisco model in Lab with Ethernet channels, because because we were creating Ethernet channels, we were creating routing ports on layer 3 switches, and when I would configure them as a trunk, Cisco model lab would crash every single time. I would try to, because what I was trying to do is I was trying to create the router on a stick topology, but with using a layer 3 switch as quote unquote the router, implementing routing ports. So what I'm saying, taking a couple of Ethernet ports, combining them into one routing port. And for some reason, when I would trunk it, Cisco Model Lab did not like what I was trying to configure, and it would crash the switch every single time. It just kept crashing the switch. But Ethernet channels are pretty neat. It's a pretty neat concept. I mean, all that switching stuff is so neat. Because you can do so many things with a layer 3 switch. Layer 3 switches are pretty stinking awesome, in my opinion. They can do so many. You can do so many different things with them. But yeah, like, so this is actually pretty funny right here. Well, what I'm running into right here, this issue. So what I'm trying to do is I'm trying to create a static route to get to the :3 net, which is this net right here for PC3 that's off of router 3's interface here. And when I try to configure it for a static route using the interface command, as you can tell, the pings fail. And this ping's going to fail. All right. And we can look at it too. So the interface I'm trying to use it on is the gig 0-2's interface off of R1. Now, if we look at our interfaces, gig 0-2 is connected to R3. Exactly, and that should be the correct interface for that command that we're using. But again, it's failing. Now, if I were to, let's go ahead and erase it now. So we'll erase that route. We'll give it the no command, and then we'll just double check IPv6 routes. Show the do show 6 routes. All right. Now we can take a look, and again, I erased that route, so that route's now gone. All right, so we've deleted that route. Now we'll recreate that route, so we'll do the IPv6 routing, and then we'll use the next hop router type. We'll use the next hop router address instead of the interfaces. All right, so we'll set up the route 2001 DB8 colon 1111 colon, that's the 3 net colon / 64. All right, via the 2001 colon DB8 colon 1 1 colon, that's the 5 colon 2. Okay. All right. So now we statically, and then we'll just check the routes again. So again, now we have that route going to the 3 net, going to the interface. So this interface from R1 to R3 here, that's using the 5 net, so the colon 5 address. All right. So we can now see if we can ping that address. So let's do a do ping. And I believe I still have this address saved. That should be the address for PC3 here. So that's the address for PC3 right here. All right. Now we'll see if we can actually ping it. And now that ping succeeds. All right. So for some reason, the static configuration for the interface is not correctly working. It's working for when we configure it for the next hop router. All right, and then we can also we'll do a do show IPv6 interface brief. And we can take a look at, so off of gig 02, all right, so that's the 5 net right there. That's what I was saying. So that's the 5 net going from R1 to R3 here. All right. All right. So again, static routing is sometimes a pain in the cookies. But for now, can this PC ping PC3? No, you can't. No. So PCs can't ping each other's yet. All right. Come over here. IPv6 route. We're gonna say 2001 colon 1 64. That's gonna be off of the colon 2001 colon 1111 . That's gonna be off of the 4 colon 1. Okay. Let me just copy this PC's IPv6 address. Copy. Let's go up 2. Do ping PC1. Let's see if we can ping PC1. And no. But we cannot. You show. Wow, it's like I didn't even take that static configuration on this one. Oh yeah, I love what DHCP does. It's amazing. Um, but for this, for instance, like OSPF, enabling OSPF on this network would make life easier. But again, you are right. You know, there is a true need for static configurations and stuff like that, and floating and floated configurations and stuff like that for failures, redundancy, and stuff like that. That's what this is mainly about, to show you that you need to implement redundancy within your network. You know what I'm saying? I guess that's what, networking is all about. Is it's just like anything else. Building airplanes, building cars, and stuff like that. It's always about redundancy. DHCP is ideal for dynamically addressing everything. I love DHCP. You know what I'm saying? I especially dealing with IPv6, trying to statically address everything in the network, my mind would explode. But via DHCP, especially DHCP version 6, it makes life so much easier with just creating addresses. And you can see that the addresses they're doing too is it's pulling off of the it's not so much creating that you're assigning the prefix. DHCP version 6, I guess, is, there's that difference too, where instead of it assigning the complete like address range, it's like you give it the prefix, give it your address prefix, and then it's still pulling off of it's still dynamically creating that addresses off of the MAC address of that network interface card, off of whatever host you're assigning it to and whatnot. And that's why we're coming up with these kind of addresses here by using the MAC addresses off of the network interface cards off of these hosts here. But again, why is this not? Why did R2 not take to our IPv6 route that we just configured it? Why don't I use Cisco Packet Tracer? I do use Cisco Packet Tracer. I use Cisco Packet Tracer for a lot of things, mainly like when we get to studying on wireless technology and stuff, we're going to be using Cisco Packet Tracer. But the reason why I'm primarily using Cisco Modeling Lab is Cisco Modeling Lab. Again, I don't know how familiar you are with Cisco Modeling Lab, but it's using real. Cisco Modeling Lab is using real iOS images. So these are actual real iOS images here. These are the same images that would be on a real Cisco device. So it's an emulator instead of being a simulator. So Cisco Packet Tracer is a simulator, which is great. I mean, I love Cisco Packet Tracer. I'll never take anything away from it. But the thing is there's missing commands. Things are just not real. You know what I'm saying? Where this is actual real. For the most part, it's real. Obviously, there's still a difference between using real gear and virtualized gear, but this is as real as I can make it for yeah. So again, I mean, you might have heard of GNS3 or something like that. This is, yeah, it's as real as possible. How's that? It's as real as possible without having a real gear. Exactly. Yeah. So let's try that again. So the IPv6, we're still in route. We'll try and get to the 2001 EV8. All right, because we don't have an actual route for that. EV8 colon 1111 colon 1 colon slash 64. And that's going to be retrieving off of the 2001 colon EV8 colon 1 colon 4 colon. So there's our static route. Okay. Now let's do a do ping paste. All right. Now we can ping PC2. Let's go over to PC1, I mean. All right. So let's copy PC2's IPv6 address. Go back here. And let's see if we can ping PC1 to PC2. All right. So now we can ping PC1 to PC2. All right. Let's go over to R3. All right. We're going to say IPv6 route. And then this is, again, we're going to the 2001 EV8 colon 1 colon. That's the one net colon slash 64. That's via 2001 EV8 colon 1. That's the 5. 1. We can do a do show IPv6 routes. All right, now we have that static route, okay, for the one net. Go back here. Let's copy this address. Go back to PC1. We'll see if now we can ping PC3 from PC1. Very good. So now we can ping. We can pretty much ping everybody in our network. Now let's make sure we can go it the other way now too as well. So PC2. Very good. Very good. Oh, thank you very well. I appreciate you stopping by today, my friend. Yeah, so I'm on 5 days a week, Monday through Friday. 5:30 p.m. Eastern Standard Time is when I usually start these streams. So I'll catch you another time. Thank you again for the follow, my good friend. You have a good night. Get some good sleep, okay? All right, so we can ping everything. We have, so we're pretty squared away now. That. Come on, don't break on me. All right, let's do a do show 6 routes again. And everything looks good. We have our statics. All right, very good. So we are in the money right now. All right. Continue on here. So I was having issues connecting via the interface command. For some reason, it just did not want to. Take for that. This command, like many facts about the static routes on R1, first show the code S. So that's exactly what we're seeing here. So the code S right here, stating that it's a static. Obviously, we have connected, local, and stuff like that. So these are our 2 static routes that we built in. All right, and again, it's the route. All right, via the next hop router's address. So the next hop router. So to get us to the 2net, so the 2net is up here. All right, we're gonna go from the DB8 11111 4-2. So the 4-2 is this next hop router's interface right here. Okay, getting us to the 2net. Same thing for the 3net. This is the 3net right here. Going off the next hop router. So this is the next hop router's interface right here. So this interface right here. Okay. All right. Yada, yada, yada. Yep. Static routes using next hop router's IP address. We just covered that. All right, example static route with global unicast next hop router's address. This example shows the internet network. But with earlier routes, remove. That is, both routers have only connected routes and local routes to begin in the example. Both R1 and R2 add the static routes to refer enable global. Both R1 and R2 add static routes that refer to the neighbor's global unicast address. R1 adds a route to for subnet 2 on the right, while R2 adds a subnet for R2 on the left. Note that the example shows both directions so that the hosts can send packets to each other. And that's exactly what we already did. So the 1net and the 2net. All right, IPv6's route command itself is relatively straightforward. Focus on R1s, which matches the local. Yep. To verify the command on R1, shown in the example, usually it lists the usual information. Show two commands. First thing, the R1s only interface static, yada. And the example, the list shows the list of the IPv6 route. Show the IPv6 route the command, which lists the router's R1 uses straight with forwarded packets provided that. Okay, if we were to do this, do show IPv6 route static. All right, it's just going to show us our static routes on R1. Okay, so these are our static routes. So we have to the 2net and the 3net. All right, that's what that's showing right there. And then again, if we wanted to get a little bit deeper information, say we wanted to take a look exactly at the 2net information, so we would do a do show IPv6 route 200 DB8 1111 to the 2net :/64. Known as static distance 1 metric 0. Route count is 1-1 share count. Routing path, so there's our routing path right there, telling us we're going to the interface on R2 here. Okay, last updated 36. I believe that's seconds. Or that might be minutes. That might be minutes actually. What are you guys doing? Same information. Yeah. All right, so we're looking good there. All right, explain static routes with link link local next hop addresses. Static routes refer to the link to the neighbor's link local addresses. Work like a little both of the preceding two styles of static routes. First, the IPv6 route command refers to a next hop address, namely the link local address. However, the command must also refer to the router's local outgoing interface. By both, the IPv6 route command cannot simply refer to a link local next hop address by itself, because of the link local address does not by itself tell the router which outgoing interface to use. And interestingly, when the IPv6 route command refers to a global unicast next hop address, the router can deduce the outgoing interface. For example, the early example on R1, as shown in the example, shows the R1 with the static IPv6 route with the next hop IPv6 address is 2000 yada. R1 can look at the IPv6 routing table, see its connected routes that include the 2001 DB8 :111 4-::2 address, and see that's connected off the route of the 0000 interface. As a result, the next hop the next hop global unicast address R1 can deduce is the correct interface. Cool. With the link local next hop address, a router cannot work through this same logic. So the outgoing interface must also be configured. And the example shows that the configuration of the static route on R1 and R2 replaces for the two routes previously named. All right. And that's maybe what we were running into issues before. So let's try that now. Let's try that on the ReNet. All right, let's do it. Show IPv6 int brief. All right, and we're going to use this link local address. And we're going to go no IPv6 route. We're going to say the 2001 PB8 colon 1111 colon, that's the 3net colon /64 via 2001 colon DB8 colon 1 colon 5. Okay, and then let's do a do. Show IPv6 route. We should have got rid of that other statically. Yep. All right, so we're good on that. All right, so now let's do IPv6 route, and 2001 DB8 colon 1 colon, that's the 3net colon /64 gig 0-2, and what's going to use that link local address. All right, now let's do a do show IPv6 route. See what that looks like now. All right, so now we have a static address using a link local. All right, off of the gig 0-2 interface. Let's go back to PC tree here. Let's get an IP address. Let's get that IP address real quick. Copy. All right, now let's do a do ping. And boom. All right, so that worked right there. That worked actually pretty good right there. So if you remember earlier, we were having issues. We were running into issues when we were just using the interface command. Now we're using the link local with the interface to create that static route here. So we have the 3net, all right, via the link local address. The link local address off of this interface, so this interface that's facing R1 here, off of the gig 0-2. Okay, so that's what we're using as our route here. All right, just as the book precedes it as. All right, and then again, you can take a look at that link local addressing that we're using. Okay, so this is the link local address that we're using here. Okay. Verify the configuration by repeating the IPv static route. Yep command. Note that the output for from both commands differ slightly in regards to forwarding the details because the new command lists both the next hop address and outgoing interface. The show command also lists both next hop and local address in the outgoing interface. Yep. All right, we took a look at that. We're doing pretty good actually. All right. All right. You might have wondered why the chapter shows examples with a serial link, knowing that most networks use fewer and fewer serial links today.
Here are some TV shows.
What was that? I did not say anything to you. The next examples discuss the issues of and show configuration options for static routes when the outgoing interface is an Ethernet interface. Okay. To configure a static route that uses a Ethernet interface, the IPv6 route command forwarding parameters should always include the next hop at IPv6 address. Okay. iOS allows you to configure an IPv6 route command using only the outgoing interface parameter without listing the IPv6, without you listing the next hop address. The router will accept the command. However, the command, if that outgoing interface happens to be in an Ethernet interface, the router cannot successfully. That's exactly why it wasn't working, and we can show that again. All right. And it wasn't. We can prove that that wasn't working. So let's erase this now. The 6 routes again. Let me show that we got rid of that. So again, we got rid of that. So now it's not listing that route anymore. All right, and then we can do the IPv6 route. All right, to the 3net 2001 : DB8 : 1111 : 3 : /64 via the gig 0-2. I do show route. Hashtag blame IPv6. What's up, Gamer Golf? IPv6 will give you a headache. So here we go. So now again, we have that route via. Now it's just via the interface, right? And we'll try to do the ping again. All right, and that ping's going to fail. All right. So again, that just confirms what was going on with what we were doing, where IPv6, yes, it will allow you to create that route via the interface. Definitely going through golf swing withdrawals. But aside from that, not bad. Just go in your backyard and just start slamming balls into your neighbor's driveway. Boop, pew, smash. Boop, pew, smash. It's funny. I used to work at a. I probably told you I was an equipment operator already. But my last gig, I worked in a recycling plant. It was an auto recycling plant. And at the end of the day, when it was all closed up, me and the guys would and all of our industrial facilities are closed due to the global bastard. Right. But what I was saying was we used to, at the end of the day, we would set up golf balls because we used to use golf clubs. It's funny, golf clubs are like, they're a perfect tool. We would use them for we would slice the heads off of them because all golf clubs are like, for the most part, most of them are aluminum based, and we would use them as pokers to empty out antifreeze out of antifreeze hoses and stuff like that, out of radiators for cars. But we would always have a whole bunch of golf clubs laying around. So at the end of the day, we used to just line up golf balls and just peg them into the yard and see how many windows we could smash from where we were standing. It wasn't the right thing to do, but it was something fun to do at least. All right. So here we go. So exactly what this excerpt of this chapter was saying, that IPv6 will not correctly route the packets if we're just using the via the outgoing interface command. So we have to add a link local address or a next hop router address to that route for it to work again. So again, let's go back. Let's erase that route again. All right. Let's confirm that we have erased that route. All right, we've confirmed that we erased that route. And then we can do the IPv6 route. IPv8 colon 11 colon 3 8 colon 1 colon, that's the 5 colon 2. All right. So we get that route back, and we have that static route back. Again, now let's do a do ping. Copy. Paste. All right. So we're back. We're back to normal. And we're able to ping the 30 net 3, whatever you want to call it now at this point. All right. To configure the IPv6 route correctly when directing packets out in Ethernet interface, the configuration should use one of these styles. Prefer the next hop global unicast address or unique local address only. Refer to both the outgoing interface and the next hop global unicast address or unique local. Refer to both outgoing interface and next hop link local address. So that's what we configured prior when we had it configured to the where is it? So that's it via, oh, that's when we removed it. Right here. So that's when, so right here when we had it configured via the interface, okay, via the interface, but we also had it, we had to add the link local address of the interface that's obviously connected to R1 here, again, for that to work, okay? So you can't just point an IPv6 address to at least over an Ethernet. Over serial, yes, you can, and that's what it was describing. Over serial, you can point an IPv6 over a serial interface and it would route. But over an Ethernet interface, it will not route if you just point that route to an interface. You need a next hop address to be able to route that, route those packets successfully via IPv6 here. All right. All right. Shows in the configuration, the top part of the figure shows details. Yep. Static IPv6 routes. I told you an NTTP joke. That timing was perfect. I once told. I'm trying to remember that joke. What I'm trying to remember that joke again. What how'd it go again? My brain has been a foggy mess lately, Gamer Golf. All right. So yes, we covered that. Static routes, static default routes. IPv6 supports a default route concept similar to IPv4. The default route tells the router what to do with an IPv6 packet. When that packet matches no other IPv6 routes, the logic is pretty basic. With no default route, the router discards the IPv6 packet. With the default route, the router forwards the IPv6 route based on the default route. Default routes are particularly useful in a couple network design cases. For example, with an enterprise network design that uses a single route at each branch office, when linked to each branch, the branch router have only one possible path over which to forward packets. In a large network, when using a router protocol, the branch router could learn thousands of routes, all which point back towards the core of the network. Okay, fine then. 5 routers walk into a bar. Who gets the car keys? The designated router. That's a good one. The designated router. He hasn't been sipping on the sauce. That's why. All his router homies been sipping on the scissor. That was good, Gamer Golf. That was good. All right. The branch router could use a default route instead of routing protocol. The branch router would forward all traffic to the core of the core network, shown in the figure. Such an example with 2 sample branches on the right and its core that sits on the left. All right, so we're all pointing back to the. So this would be like the almighty. This would be like in IPv4, the almighty 0 net. So this is IPv6 equivalent to the almighty all 0 default network. So it'd be the : /0. All right, address. All right. Using static default routes at the branch, forward back to the core, yada yada. To configure a static default route, use the same rules already discussed in this section of the chapter, but use the specific value to note that the router as a default route. Taken literally, the 2 double colons is the IPv6 equivalent to all zeros, and the /0 means the prefix length is 0. The idea mirrors the IPv4 convention, referring to the default route as the all zeros net. Otherwise, just configure the IPv6 route command as normal. All right. So in the show, all right. So that's again, it's going out the serial interface with IPv6. With IPv6, the router displays the default a little more cleaner than IPv4. The show IPv6 route command simply includes that the route in the output command along with other routers. Show in the example the : /0 list denotes that the route as a default. All right, as a default route. Okay. All right, static hosts, static IPv6 host routes. Both IPv4 and IPv6 allow the definition of static host routes. That is a route to a single host IP address. With IPv4, the routes use a /32 mask, which identifies a single IPv4 address in the IP route command. With IPv6, a /28 mask identifies a single host in the IPv6 route command. Okay. A host route follows the same rules as a route for any IPv6 subnet. For instance, if you refer back to the figure in 2-3, the host sits on the right of the side. Early example showed our R1 static route before. The subnets in which host B resides, for example, the routes for R1 in the example, yada, yada, yada. To create a host route on R1, refer to host B's specific IPv6 address. Just change those commands to refer to host B's entire IPv6 address. All right, with the prefix of 128. Okay. The example shows two sample host routes for R1, both define host routes IPv6 addresses. One route uses the R2's local link address as the next hop address, and one route uses R2's global unicast. Okay. Yep. All right, so floating static. So again, floating static. That's where we're going to be implementing OSPF version 3. And again, the reason for a floating static is almost as a redundancy in your network configuration. All right. Next, consider the case in which a static route competes with other static routes or routes learned by a routing protocol. For example, consider the topology shown in the figure, which shows a branch office with two wide area network links. One very fast. Have a good weekend. Did Mad Max kick your butt in Fortnite over the weekend? I don't know. We never got a chance. We never got a chance to play any Fortnite. He would have whooped me if we had played. I end up Sunday. I didn't end up streaming Saturday. I ended up streaming on Sunday, early Sunday morning too, and I end up. It was a while ago. I had my older sister had dropped, and that's what you're seeing in the background too. You probably can't see it, but you can almost see it. I got a 3D printer in the background that I set up a while ago. It took me about 7 hours to actually put the thing together, but it was probably about 4 or 5 weeks ago that I had streamed putting it together, but I couldn't get it. I couldn't get the table to level out and stuff like that, and I couldn't get it to actually work properly. So yesterday morning, I was like, you know what? Let me just get this thing up and running again, and to see if we can actually cut a print. So we spent some time. We got the table leveled out. We got it to cut a print. This was actually the first. This was the first print. I don't know if you can see it. So the cute little doggy. This was the first print that we got to cut. Guys, what do you keep doing with the pasta? And then we got it to cut a second print right here. His little kitty cat. And then today, I have some ideas that what I want to do with it too. Today I jumped on Blender. Because I've done some 3D stuff with Blender and stuff like that before in the past. But what my older sister told me is I can cut STL files out of Blender and then put those into I keep forgetting the name of the program. What is it called? Right here. Yeah, UDMake Cura. I can dump those files into Cura, and I can cut a print from what I've created in Blender, and then I can print those. So today, just to see if I could do it real quick, I made just some 3D letters on Blender, and I cut them out. They came out pretty good. I was trying to make like a business card. I mean, it's going to be hard for you to see it, but I just cut some letters. You know, I made them in Blender, and then I dumped them into Cura, and then I cut them with the 3D whatever slice cut, whatever you want to call it, on the 3D printer, and they came out decent. So what my idea is, what my thought process is I want to make like some visual aid stuff for the whiteboard. So I'm gonna get back into Blender. We're gonna make some like just like, like what you would see for like a router image. We're gonna make like a route. I'm gonna design a router image, have it, R1, whatever, with the arrows. We'll make like R1, R2, R3, and then we'll make switch, SW1, SW2, SW3. We'll make a cloud image and stuff like that. When I want to make it big enough, and then have it so I can put a magnet on it in the back of it. And then when we do whiteboard and stuff, instead of me always drawing out routers and stuff like that and switches, we can use those on the whiteboard, and then use those as a visual aid. We'll color it, stuff like that, to make it look nice. But that's an idea I have for that. I wanted to do was that as well, was create more visual type aids and stuff like that. Because what I'm trying to get at is, how can I share that with you guys too as well? So if, say, we create something and something's really neat, something catches on as a cool visual aid, or something that could help everybody like study and stuff like that. Like maybe like the like the subnetting table there, the 128, 64, 32, that table right there, some table like that. Maybe we can cut a table like that as a visual aid prop that, I can cut a whole bunch of these prints out and maybe send them out to, some of my, special fans and stuff like that have been showing me love this entire time. So I have some ideas that I'm trying to get, like, see if I can figure that out, see if I can, and get down to it, just to add some more creative, just to add some more flavor and creativity to this actual stream here. You know what I'm saying? That I think that will aid for studying and stuff like that, and just keep the interest in the stream going too as well. So that's kind of like my thought process where I'm going with that. More to come, obviously, like everything else that I've been doing thus far with the stream. But yeah, so that was the weekend. All right. Example, consider that in the topology shown in the figure, which shows a branch office router, 2 WAN links, one very fast gigabit Ethernet link, and one very slow link but cheap. The T1 in the design, this network uses OSPF version 3 to learn OSPF 6 routes over the primary link. Learning a route for the subnet. Hold on 1 second, guys. What are you doing? No. Start getting up in there? I'll let go of it. Now you know there's nothing. Excuse me. All right. In the design, the network uses yep, then the routes. R1 also defines a static route over the backup link. Yada yada yada. Exact same. All right. So this is a similar concept to how OSPF, how we were doing floating routes with OSPF and IPv4. All right. All right. Using floating static routes key to key subnet, yada yada yada. Yep. All right. iOS considers a static route better than OSPF learned routes by default due to the administrative distance. iOS uses the same administrative distance concept as a default for IPv6 as it does in IPv4. As a result, the IPv6 route over the lower path will give you an administrative distance of 1. Again, just like it was in IPv4. And OSPF learned route over the top will give you an administrative distance of 110, exactly the same as IPv4. R1 should use the lower path to reach the subnet. 2001 DB8 1111:7. Yep, in this case, which is not the intended design. Instead, the engineer prefers to use the OSPF learnt route over the much faster primary link and uses the static route over the backup link only as needed if the primary link fails. Okay, so again, because this was statically configured, that has a lower administrative cost. So the router by default will use this static link, okay, instead of this OSPF learnt link over here. Even though this link is a faster link, it's still going to use this static link right here, okay? Because of this link has an administrative cost of 110, but this static link has an administrative cost of just 1, okay? All right. Yep. All right, to implement the IPv6 floating static route, just add the just override the default administrative distance of the static route. By default, the value larger than the default administrative distance of the router protocols. For example, IPv6 route yada 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 via the 2009, not 2009, but the 9 route, and given an administrative cost of 130. All right. So that command right there, giving it the cost of 130, following by the actual static route. So the static route command pretty much right here, with the administrative cost command right there. All right, all-in-one will do exactly that. So again, we're giving it the cost of 130 now. That meaning that, again, greater than the cost of the administrative cost of OSPF learnt route, which is 110. All right, so then once that's configured, it will start using the OSPF learnt route. All right, as long as the primary link stays up, in OSPF on R1 learns that the route yada yada yada. OSPF administrative cost is 110. R1 ignores the static route, whose administrative distance is explicitly configured as 130 now. All right. Finally, note that both the show IPv6 route and the show IPv6 route yada 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 command list the administrative distance. The example shows the sample matching this most recent example. Note in this case that the static route is using IPv6 routing tables. Okay, so again, here is that the cost and then the metric. All right, the administrative cost and then the metric. Okay, so we set the distance to 130. Okay, obviously the metric is still 0. All right, static. All right, but the distance now is set to 130. All right, so here's our code for our administrative cost distances. So connected routes 0, static 1, NDP 2, ERGRP 90, OSPF 110, RIP 120, unknown or unbelievable 255. Okay. Troubleshooting static IPv6 routes. IPv6 routes have the same potential issues and mistakes as do in static IPv4 routes, as discussed in Chapter 16. However, IPv6 routes do have a few small differences. The last part of the static route contents in the chapter looks at troubleshooting IPv6 routes. All right, reviewing many of the same troubleshooting rules applied to IPv4 static routes while following the details specific to IPv6. Okay, the topic breaks static routes troubleshooting into two perspectives: cases in which the route is in the routing table but is incorrect. Oh, I'm dude. Yada yada yada. All right. Troubleshooting incorrect static routes that appear in IPv6 routing tables. A static route is only as good as the input typed in the IPv6 route command. iOS checks the syntax of the command, of course. However, iOS cannot tell if you choose the incorrect outgoing interface, incorrect next hop address, or incorrect prefix length in the static route. If the parameters pass the syntax checks, iOS passes the IPv6 route command into the running configuration file. So that's just pretty much saying that the iOS is not going to specifically check if the next hop address and the next hop prefix or the interface is correct. It's just if it passes the syntax for the actual command, it's going to just pass that configuration right to your running configuration. All right. And if it's incorrect, it's incorrect. As long as it passes the syntax check, meaning if you checked all the boxes while you're entering in that configuration, then yes, it's going to pass, but it may not be correct. It may not be correct. All right. And that's just what that is saying. Then if no other problems exist, as discussed in the next heading, iOS puts the route into the IPv routing table, even though the route may not work because of the poorly chosen parameters. For instance, an exam question might show a figure with the router having a address yada yada yada, and the neighboring router with the address of yada yada yada. If R1 lists the static route with the command IPv6 route 3.3.3 yada 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 via the 2001, the command would be accepted by the iOS with the correct syntax, but it would not be effective as a route. Note that the command lists R1's address as the next hop address, and R1 cannot use its own IPv6 address as the next hop address. iOS does not prevent the configuration of the command. However, it allows the command to be adds to the route in the IPv6 routing table. But the route cannot possibly forward a packet correctly. Okay. When you see exam questions that have static routes, you'll see them in the output of the show IPv6 route. Remember that the route may have incorrect parameters. All right, check for these types of mistakes. So prefix length, does the IPv6 command reference the correct subnet ID, prefix, and mask? If using an XHOP IPv6 address, that is a link local address. All right. Is the link local address an address on the correct neighboring router? It should be the address on the other routers or on the shared link. All right. Does the IPv6 route command also refer to the correct outgoing interface on the local router? Step 3, if using NextHop router IPv6 address, that is the global unicast or unique local address, is that address correct? Correct unicast address of the neighboring router. All right. If referring to the outgoing interface, does the IPv6 router command reference the interface of the local router? That is the same router where the static route is configured. This troubleshooting checklist works through a various case in which iOS would accept the configuration of the static IPv6 route, but the route would not work because of the incorrect parameters in the context. It helps to see a few examples in the show command. So all the examples. All right. The example shows 5 IPv6 route commands. All have correct syntax, but all have one incorrect value. That is, the route will not work because of the type of problems in the troubleshooting checklist. Look for the short comments at the end of each configuration command to see what is incorrect. Okay. So we have the wrong prefix. All right, wrong neighboring link. Okay. Missing outgoing interface. Remember when we're using a link local address, we also have to use the interface command too as well. All right, we have to give it an interface too as well. Wrong neighboring address, wrong interface on R1. All right, all these incorrect examples have the correct syntax, so these would all pass. These would all be passed through the syntax properly, but again, they're all wrong. All right, and would be added to R1's IPv6 routing table. if configured on R1. However, all have flaws working through the examples. All right. Step 1, the prefix has a typo in the fourth quartet. 33 instead of 3. Again, it's just going through that. The figure shows, yep. The key takeaway for this section is to know that a route in an IPv6 table may be incorrect due to the poor choices for the parameters. The parameters should always include the neighboring router's IPv6 address, but the local router's interface type / name. In all cases, the correct prefix length, the fact that the route is in the IPv6 routing table, particularly a static route, does not mean it's correct. Okay. Next note of the 5 example commands, iOS will accept all of them. Besides the third one, iOS can notice in this case of omitting the outgoing interface in the next hop router link local addressing. All right. So it's just saying that it'll notice that they didn't add the link local address here. All right, let's continue on. The static route does not appear on the IPv6 table. The preceding few pages focus on IPv6 static routes that show up in the IPv6 routing table, but unfortunately have incorrect parameters. The next page looks at IPv6 routes that have correct parameters, but the iOS does not place them in the IPv6 routing table. When you add a IPv6 route command to the configuration and the syntax is correct, iOS considers the route to be added to the IPv6 routing table. iOS makes the following checks before adding the route. Note that the iOS uses the same kind of logic as IPv4. Yada, yada, yada. Yep. All right. The neighboring discovery protocol. All right. Let's have a discussion about this. Similar to ICMP for IPv4, IPv6 defines ICMP protocol for IPv6, ICMP version 6. However, ICMP version 6 reaches further than ICMP version 4, pulling in functions done by other miscellaneous protocols in IPv4. For instance, with IPv4, ARP works as a separate protocol. With IPv6, the Neighboring Discovery Protocol, NDP, a part of ICMP version 6, performs the same functions. As it turns out, routers play a key role in several NDP protocol functions. So this first major section of the chapter explains a few of the functions of NDP, RFC 4861, some of those NDP functions. All right. Neighboring MAC discovery. An IPv6 local area network-based host will need to learn the MAC addresses for other hosts in the same subnet. NDP replaces IPv4's ARP, providing a message that replaces the ARP request and reply message. Router discovery, hosts learn the IPv6 address of all available IPv6 routers in the same subnet. Slack, when you hold on, what's up? All right, I was gonna get him. Love you back. All right, Slack. So when using stateless address auto configuration, Slack, the host uses NDP messages to learn the subnet prefix used on the link plus the prefix length. Okay. Dad. By using IPv6 addresses, hosts use NDP to perform duplicated address detection. So duplicate address detection. Okay, process to ensure that no other host uses the same IPv6 address before attempting to use it. Okay. Discovering neighboring link addresses with NDP, NS, and NA. Okay, NDP replaces IPv4's ARP using a pair of matching solicitations and advertisement messages. The neighboring solicitation, the NS, and the neighboring advertisement, NA message. Basically, the NS acts like the IPv4's ARP request, asking the host for with a particular unicast IPv6 address to send back a reply. The NA message acts like the IPv4's ARP reply, listing the host MAC address. So we have the NS, which is acting as the request, and NA acting as the reply. All right, so we have the NS, the request, and then the NA, the reply. Okay. All right. The process of sending the NS and NA messages follows the same general principle. Purpose with the IPv4's ARP. The NS message asks for the information. The NA supplies the information as a summary in this list. Neighboring solicitation. All right. This message asks the host with the particular IPv6 address, the target address, to reply with the NA message that lists its MAC address. The NS is sent to the solicited node multicast address associated with the target addresses. So the message is preceded only by the host whose last 6 hex digits match the address that is being queried. All right, neighboring advertisement. This message lists the sender's IPv6 address and MAC address. It can be sent in a reply to an NS message. And if so, the packet is sent to the IPv6 multicast address of that host that sent the originating NS message. A host can also send a unsolicited NA announcing its IPv6 address and MAC address, in which case the message is sent to all IPv6 addresses in the local scope multicast address. All right. With NDP, the word neighbor refers to the fact that the devices will be in the same data link, for example, in the same VLAN. All right. All right. In the figure, shows an example of host PC1 uses the NS message to learn the MAC address. MAC address used by another host. The NS message lists a targeted IPv6 unicast address with the implied question, "What is your link address?" The NA message in this example sent back to the original host that the question of the link. All right, let's actually, you know what? Let's see if we can capture. See if we can capture some of these. See if we can capture one. We have CDP. DHCP. Know what we can do. Let's do this then. Copy. Go back to the first. I would probably have to be a new. Let's do this then. Let's add a new host to this link here. It's probably PC 1-1. On. I want to just capture some of these NDP messages on these links here. I don't think we're gonna get any on this one. Yeah, let's clear that. You know, let's download this packet capture real quick. Let me more. And then we'll open up Wireshark and we'll take a look at this in Wireshark. Not DHCP messages. It's gonna finish up right now. Download that. Just scenes real quick. I'm just gonna open up Wireshark real quick, guys. I'm gonna open this up in Wireshark, so then we can take a look at it together. All right, so we got Wireshark opened up, and we can take a look at. All right, so there we go. So we got neighboring solicitation, we got neighboring advertisement. So there's those two messages right there. All right. And I also on the Discord as well. I'm gonna put this. I'll upload this up to the Discord too. So let's go to where is it? Packet capture. IPv6 lab. And this is today's date is 01/01/25/2000. All right, so you guys can take a look at that too. It's up on the Discord too. All right. So here we go. All right. So we have destination. All right, so it's using the FF. All right, so it's using the multicast address. Yeah, so I am IPv6 multicast. So the FF. So it's using the dest as the multicast address. Okay. Source. Again, it's looking for layer 2 type of information. There we go. Type right there. Neighboring solicitation. All right. Target address. All right. And then we'll go down to this one. This is the neighboring advertisement now. Cool stuff. There's some more. All right, so there's some more in that ICMP version 6. Okay. So we have some more neighboring solicitations, some more advertisements, so on and so forth. Just keeps on going back and forth. All right. And then we obviously have some DHCP messages, some CDP messages in there as well. So yeah, so this this packet's up on the Discord. So if you want to take a look at this capture, you guys are more than welcome to. All right. All right. So we took a look at that. Oh, have a good night, Gamer Golf. I'll talk to you later, man. Enjoy the pasta. You know it. That's step 1 on this particular example. PC1 sends solicited to PC2's MAC address. The first looks at the NDP table, the equivalent IPv4 ARP cache, exactly. It does not find the MAC address for the IPv6 address. So at this step, PC1 sends the NDP NS message to the matching solicited node of the address, yada, yada, yada. Or the, this would be the multicast address right here. All right. Only IPv6 host whose address ends in the 00:0022 will listen to the solicited node multicast address resulting only on a small subnet of those hosts on this link will process that receive ND neighboring discovery protocol neighboring solicitation message. Yes, neighboring solicitation message. Okay. At step 2, the PC2 reacts to the NS. PC2 sends the neighboring advertising message in reply to listing PC2's MAC address. PC1 records PC2's MAC address in PC1's NDP table. Here's an example of the IPv6 neighboring table on R3, as seen originally back in the figure. In this case, R3 has learned the MAC address of R1's wide area network interface, both its global unicast address as well as this link local. All right, so let's do that. Let's take a look. R1. All right, let's do show. What is that command? Show IPv6 neighbors. Yep. IPv6 neighbors. All right, just like we would look at the ARP. All right, so here's all of our neighbors right now. All right, state, stale, link local addresses, link local addresses right there. All right, and here's off of which gigabit, which interfaces are those. Um, excuse me. Which interface are these neighbors off of right here? Okay, very good. All right. To view a host NDP stable, use the command for the Windows. It's the net sh interface. So let's do this on the show. So let's do this on the actual Linux machine. So it'll be IP neighbor show. This might not have it. Might not. Yeah, it doesn't have it. It's fine. These are little Alpine Linux boxes, anyways. It's pretty reason why it doesn't have it on it. All right. Discovering routers with NDP, RS, and RA. IPv4 host use the concept of a IPv4 default gateway or default router. When the host needs to send a packet to some IPv4 routes subnets other than the local subnet, the host sends the IPv4 packet to the default router, expecting the router to be able to route the packet to the destination. Note that the host either statically sets the IP address of the default gateway or learn it from several from a server called the Dynamic Host Configuration Protocol, DHCP. Yes, DHCP server. Okay. IPv6 uses the same concept of default gateways, but it improves this method for hosts to learn the identity of possible default gateways using NDP. NDP defines two messages that allow any host to discover all routers in the subnets. So we have the router solicitation. This message is sent to all IPv6 routers local scope multicast address, the FF2 : 2. All right, so that this message asks all routers on the link local only to identify themselves. The router advertisement. This message is sent by the routers list many flags, including the link local IPv6 addresses on the routers. When it sends it when sent in response to the RS, it flows back to either the unicast address on the IPv6 host that sent the RS, or to the all IPv6 address host, the FF02. The routers also send our RA messages without being asked, sent to all IPv6 hosts and multicast address, the F00. So, okay, let's take a look at that now real quick. Let's take a look at this link. Start capturing some packets off of this link here. So let's go here. Let's drop down. Broke a little bit. It's fine. So let's ping 2001 DB8 1111 colon 4 colon 2. All right. We'll download these. All right, stop. You can download those. Let's open up Wireshark. advertisements. I'm just trying to find some of those RA and RS messages here. Let's see them specifically. Identify yourself, and I am Matt. So it's just identifying. It's just identifying messages. I was just looking to see if we were to get these addresses to populate on that captcha. All right. IPv6 allows multiple prefix and multiple default routers to be listed in the RA messages. The figure shows just to show one of each for simplicity's sake. IPv6 does not use broadcast, but it does use multicast. In this case, the RS messages flow to all routers' multicast address, the FF02::2, so that all routers will receive this message. It has this the same good effect as a broadcast in IPv4, without the negatives of a broadcast address. In this case, only IPv6 routers will spend any CPU cycle processing the RS message, and IPv6 hosts will ignore this message. The RA message can flow either to a unicast IPv6 address of the PCs or all host nodes and FF02 address. So that's just stating that because of how it's using this multicast addressing, hosts are not going to process this message. Only the routers will be processing these messages, the RS and the RA messages. Note that while the figure shows hosts can ask to learn about any routers, routers also periodically send unsolicited RA messages even without an incoming RS. When routers send these periodically RA messages, they basically advertise their details about IPv6 on the link. In this case, the RA messages flow to the FF02::1, all nodes IPv6 address, multicast addresses. All right. Only got a little bit left, right? Yeah, only got a little bit left. All right. Using Slack with NDP, RS, and RA, both IPv4 and IPv6 support the idea of dynamic address assignment for host via the DHCP protocol, dynamic host configuration protocol. To find an address to use with DHCP, the DHCP client sends the messages to the DHCP server. The server assigns a correctly unassigned address to the correct subnet for the endpoint host to use. This project relies on DHCP client functions in each device and DHCP servers configured and working in that network. IPv6 supports an alternative method to IPv6 hosts to dynamically choose an unassigned IPv6 address to use a process that does not require a server like a DHCP server. The process goes by the name of stateless address auto configuration. So stateless address auto configuration. So Slack. Slack uses a simple 3-step process that begins by learning the prefix line as shown in the figure. The steps are the following: learn the IPv6 prefix used on the link for any router using NDP RS messages. Build an address from the prefix plus the interface ID. Choose either to use the EOI-64 rule or as a random value. Before using the address, first use the DAD, so the duplicate. So DAD, before using IPv6 host, use the NDP to perform duplicate address detection. So DAD, duplicate address detection process to ensure no other host can use the same IPv6 address before it's attempting to use it. Okay. All right. Yep. Build an address. Yep. Before using the address, first use DAD. So the duplicate address detection. All right. To make sure that no other host is already using that same address. Okay. Shows the structure of the IPv6 address created with Slack using step 1, step 2. Process next topic details, the third step. All right. Discovering duplicate address using NDP and NS and NA. IPv6 uses the duplicate address detection, so DAD, process before using a unicast address to make sure that no other nodes on that link is already using the address. Hosts use DAD not only at the end of the Slack process, but also at any time that the process at the host interface is idolized, no matter whether using Slack or DHCP or static address configuration. When performing DAD, if another host is already using that address, the first host simply does not use the address until the problem is resolved. Cool. All right. The term DAD refers to the function, but the function uses NDP NS messages. Basically, a host sends NS messages from its own IPv6 address. No other host should be using that address, so no other host should send any NDP NA in reply. However, if a host already uses that address, the host will reply with the NA, identifying a duplicate address of use of address. And the figure shows an example. PC1 utilizes and does a DAD check, but PC2 happens to have already been working and already using the address. The figure shows the following steps. PC1 uses the address, yada yada yada, must use DAD. PC1 sends the NS message listing that PC1 now wants to use the yada yada address as targeted. PC1 receives the NS, sees that PC2 already is using its own address and sends an NA back. PC1, on receiving the NA messages for its own IPv6 address, realizes a duplicate address. All right. So we just realized we have duplicate addresses in our topology here. Hosts do the DAD check for each other other unicast addresses. Link local addresses include both when the addresses in the first used in each time the host interface come up. This NDP summary, this chapter explains some of the important functions performing by NDP. NDP does more than what is listed in the chapter, and protocols also for additional and other functions. So NDP might continue to grow over time. For now, use the table as a study reference for the 4 NDP process discussed here. So we have router discovery, prefix discovery, neighboring discovery, duplicate address. Okay, so router discovery, link local IPv6 address on a router, prefix and length discovery, prefix and associated prefix length used by local links. Neighbor discovery, link local addresses, all right, for example, MAC addresses used by other neighbors. DAD, duplicate address detection, simple configuration, whether unicast is already being used. So we're just looking to see if we're sharing a similar address with somebody else in our topology here. So key terms that we went over was IPv6 host routes, local routes, IPv6 local, IPv6 administrative distance, same thing as it was in IPv4, and IPv6 multiple scope. Okay. All right, let's get over here. Let's come over to edit config. Let's fetch these. Let's go ahead and fetch these configurations. That way we can upload these to Git real quick, guys. This will just take a minute. Oh, I did that again. I always do that for some reason. I always forget to rename these labs. Name this just real simple. IPv6 static routing. Skip the lab date. So today's 1/25/2021. Okay. We can upload this other, that to, and 6 static lab. One, 5/21. Get that with the dash 2. Okay. So we got the two lab captures. So we got the two lab captures, guys, that we went over today in this lab, and we also, again, we have our we have the actual lab on Git too as well, guys. So if you guys want to take a look at that, again, you guys are more than welcome. Trying to make sure you guys have as much information as well as you guys could possibly need. There's the Discord link right there, guys. Again, if you're more than welcome to join the Discord, and that's where you guys can get all of this information that we went over today. Okay, so we have the CML lab. Again, when you take a look at that on Git, you don't need a Git account or nothing like that. You can it's just so you guys can take a look at the actual configuration that we did today. All right, and then again, you guys are more than welcome to take a look at the packet captures that we did too as well. So if you got Wireshark, take a look at those packet captures that we just did too as well. Okay. All right. All right. Let me just stop this lab. We saved everything. We can turn that lab off for now. All right, guys. So let me turn on some music. You. All right, guys. You guys have been awesome as always. You guys have a great night. Let's go raid somebody. Say hello. Who do we want to go say hi to? Who's on right now? Let's go say hi to my boy, Master. Maestro. And then, oh, there we go. All right, let's go check out my good friend. All right, he's awesome. You guys are definitely like him. Make sure you guys drop him a follow, and I'll see you guys back here tomorrow night. All right, guys. For now, you guys have a great night, and thank you very much for joining me tonight, guys. All right.